So the aim of this presentation is to give you an overview of the fundamental engineering principles and design criteria behind the development and operation of acoustofluidic resonators for applications in the manipulation and stimulation of cells and in some cases tissues. So over the course of the talk, I'll be first providing a high-level general definition of some acoustic principles which are required to understand the operating principles of an acoustofluidic resonator. I will then introduce the acoustic radiation forces acting on small particles within a standing sound wave field. I will then introduce acoustofluidic resonators, their design criteria, manufacturing principles, as well as some representative applications in particle and cell manipulation. I will provide a very brief introduction to acoustic streaming in acoustofluidic systems, and finally provide some examples of how acoustofluidic systems can be used in therapeutic applications. So let's start by providing a definition of acoustofluidics. So acoustofluidics is often referred to as the integration of acoustics and microfluidics, whereby an ultrasound source is typically coupled with a microfluidic device, which is a fluid-filled cavity where at least one of the characteristic dimensions is in the order of few micrometers. Acoustofluidics is also often defined as the ultrasound-based external forcing of microparticles in microfluidics. And this is a more application-specific definition, which reflects the fact that many acoustofluidic systems have been designed and manufactured, particularly with the aim of manipulating particles of biological cells for a variety of applications, and we'll be covering some of these applications later on in the talk. So let's start by providing some fundamental acoustical definitions. This is not meant to be an exhaustive description, and I strongly recommend going through Professor Robin Cleveland's talk, which describes in much greater detail the principles of ultrasound propagation. So sound waves are longitudinal waves, whereby longitudinal waves are characterized by the fact that the fluid particles move in a direction which is the same direction of the wave propagation. So if we consider the case of a gas-filled pipe, which is driven by a piston which undergoes an oscillatory motion, as you can see by focusing at the piston surface, the gas particles undergo compression, so regions of high pressure, as well as rarefaction, which is regions of low pressure. And this compression and rarefaction propagate along the pipe. Interestingly, despite the particles undergo this kind of backward-forward motion, there is no net fluid flow of the medium as a result of the wave propagation. We often consider pressure waves in the form of sinusoidal waves because they are relatively convenient to characterize from a mathematical point of view, and they can be characterized by introducing a series of parameters and variables, such as, for example, the wavelength, which is the distance in meters between 2 points at the same phase, for example, 2 peaks here in this image, the speed of sound, c, in meters per second, the period t, which is the duration of a cycle in seconds, and the frequency, which is the number of cycles per second in hertz. So these quantities can be related to each other. For example, the wavelength can be defined as the speed of sound multiplied by the period, or the speed of sound divided by the frequency. If we consider the case of an acoustofluidic resonator, the fluid medium can be approximated as water, which has a speed of sound of approximately 1,500 meters over second. Typical ultrasound frequencies for these resonators are in the order of 0.5 to 50 megahertz, which in turn leads to a wavelength of the ultrasound wave in the range of 0.03 to 3 millimeters. In the context of this presentation, we'll treat ultrasound waves as longitudinal waves, and in some cases also as plane waves. Where a plane wave is a wave where quantities vary along the direction of wave propagation as well as over time, but they are constant over a plane which is perpendicular to the direction of wave propagation. So a parameter which defines the resistance that a medium offers to the propagation of a sound wave is the characteristic impedance of a material. For plane progressive waves, it is defined as the product between the material's density in kilograms over meters cubed and the material speed of sound in meters over second. So the characteristic impedance is a useful parameter to also determine how a wave, a sound wave, actually behaves when it travels through a certain medium, as well as when it encounters the interface between two different media. For example, let's consider an incident wave, which is traveling through a medium 1 with an acoustic impedance Z1 equal to ρ1 C1, which encounters an interface with a second medium 2 with an acoustic impedance Z2 equal to ρ2 C2. What is likely going to happen is that once the incident wave encounters the interface, and this is the case of kind of a normal type of interaction, part of this wave will be transmitted from the second medium, and part of this wave will instead be reflected. And the extent of reflection and transmission can be determined through certain specific parameters, which are of some practical utility, for example, when designing an acoustofluidic resonator. And these are, for example, the pressure reflection coefficient, which is defined as Z2 minus Z1 over Z2 plus Z1. And the pressure transmission coefficient, which is defined as 2Z2 over Z2 plus Z1. They are defined as pressure coefficients because they relate the pressure of the reflected and transmitted waves to the pressure of the incident wave. And as you can see, impedance mismatch between the two media will likely result in a relatively significant component of reflected wave. On the other hand, the closer the characteristic impedance of the two media, the greater will be the transmitted component. So let's now consider a slight modification of the previous domain that we presented earlier. So we have a similar configuration with a gas-filled pipe driven again by a piston which undergoes an oscillatory motion, but the end surface of the pipe in this case is a rigid boundary. So what happens is that the compression and rarefaction propagation from the piston towards the right-hand side, in this case, will encounter a rigid boundary. So that incident wave is reflected backwards at the rigid boundary, and there will be an interference between the incident wave and the reflected wave. The result of this interference are the displacement and pressure fields reported here. Let's focus first on the displacement field. As you will see differently from the case of a traveling wave, in this particular case, there are regions in which particles undergo a very small displacement, in some cases zero displacement, and regions whereby particles undergo a much greater displacement. So regions of zero displacement, such as the red dot here, are referred to as displacement nodes, and regions of maximum displacements, such as the other red dot on the right-hand side here, are referred to as displacement antinodes. And as you can see, the displacement at the antinode can be positive when the fluid particle is moving towards the right-hand side, or negative when it's moving towards the left-hand side. Let's focus now on the pressure field. Okay, so, and let's focus particularly on a region which is located nearby the displacement node. So this region here. So as you can see, when the particles, the fluid particles in proximity to the node tend to move towards the node, the local density of the medium increases, which results in greater pressure, in an increase in pressure. Vice versa, when the particle tends to move away from the displacement node, the pressure reduces as the local density reduces. So this region of maximum pressure, whether it's positive or negative pressure, is referred to as a pressure antinode. Vice versa, regions of zero pressure, which correspond to maximum displacement, so which corresponds to displacement antinodes, are referred to as pressure nodes. So in summary, pressure nodes correspond to displacement antinodes, and pressure antinodes correspond to displacement nodes. So when our driving source of sound wave is represented by an ultrasound transducer, which can generate pressure wave with frequencies greater than 20 kilohertz, then the generated standing wave field is referred to as ultrasonic standing wave field. But the considerations that we made previously are valid also for an ultrasonic standing wave field. And again, in a standing wave field, we'll be able to determine pressure antinodes and pressure nodes, as well as displacement nodes and antinodes. It's also important to note that the number of nodes and antinodes of a standing wave field will vary depending on the resonant frequency. So let's consider now the case of a microfluidic device which contains a medium with cells in suspension. And in particular, in this case, cells are euglena cells, which are used as a cell model. So these cells are uniformly distributed in the absence of ultrasound exposure, but when an ultrasonic standing wave field is generated within the fluid cavity, you will notice that cells will tend to move towards a specific region of the fluid cavity. And when the frequency of the ultrasound is changed, the number of these regions where cells are manipulated to can actually vary. So what is that is driving euglena cells towards these specific locations? Are the so-called acoustic radiation forces. So these forces are generated by the nonlinear interaction between the acoustic field scattered by the particle and the standing wave field itself. And this ability of manipulating particles or cells using acoustic radiation forces forms the basis of a technology which is referred to as acoustophoresis. So let's try to understand what are the key parameters which will determine the magnitude, the amplitude of the acoustic radiation force. Before doing that, we need to make some assumptions. We should consider that our particles suspended in the fluid have a small radius, so a radius which is much smaller than the wavelength of the ultrasound wave, and also that the medium surrounding the particle has negligible viscosity, so is an inviscid fluid. Let's also consider that the particle has a certain value of density and compressibility, as well as the medium has corresponding values of density and compressibility. But the compressibility is defined as the relative change in volume upon application of a change in pressure. So an expression for the acoustic radiation force is reported here. We won't go through the mathematical derivation of this expression, but I'd like just to focus on the key parameters that affect the magnitude of the radiation force. One of such parameters is the volume of the particle. So greater volumes will result in greater radiation forces. Another important factor is the spatial gradient of the time-averaged acoustic pressure squared, as well as the spatial gradient of the time-averaged acoustic velocity squared. You can also see that in these equations, there are two parameters defined as F1 and F2, where F1 depends on the ratio between the particle compressibility and the medium compressibility, while F2 depends on the ratio between the particle density and the medium's density. So overall, the magnitude of a radiation force will strongly depend on the particle characteristics, particularly its volume, density, and compressibility, as well as the density and compressibility of the surrounding medium and the properties of the acoustic field, field applied within the fluid medium. So if we assume that our standing wave field is planar, so one-dimensional, we can determine a relatively simpler expression for what is referred to as the primary axial radiation force. So this radiation force is defined as axial because it acts in the same direction of the ultrasound propagation. So let's have a look first at our fluidic domain. So we have an half-wave resonance established within a fluid cavity, and this is defined as half-wave resonance because the thickness of the fluid layer in the direction of the ultrasound propagation corresponds to alpha wavelength. So as you can see, we will have a minimum pressure here in the center, so a pressure node, and two pressure antinodes at the interface between the medium and the walls and the rigid walls. The ultrasound propagates in the direction of the Z coordinate in this case. So the expression here provides a quantification of this axial radiation force and depends upon a series of parameters and variables. So let's define some of them first. For example, the wave number, K, is defined as 2 pi over the wavelength of the sound wave, which is also equal to 2 pi multiplied by the frequency. EAC is the acoustic energy density, which is defined as the acoustic pressure squared over 4 times the density of the medium multiplied by the speed of sound of the medium squared. And if we have a look at now at the effect of these individual variables on the magnitude of the radiation force, what we can see again, as for the previous expression, is that the magnitude of radiation force scales with the cube of the particle radius. So the particle radius has a strong effect on the radiation force. It also depends on the position of the particle along the Z coordinate. So particles that are at different initial positions will be subject to different intensity of radiation forces. It depends on the acoustic energy density and on the wave number. So greater frequencies will result in greater radiation forces. And finally, it also scales with this parameter phi, which is defined as the Acoustofluidic contrast factor. As you can see, that this is the mathematical definition of the contrast factor, which depends upon the ratio between the density of the particle and the density of the medium, as well as the ratio between the compressibility of the particle and the compressibility of the medium. So this contrast factor will affect the magnitude of the radiation force as well as the direction of the radiation force. So if the contrast factor is positive, particles will be manipulated towards a pressure node. If it's negative, they will be manipulated towards a pressure antinode. So in the first case, as I said, particles are manipulated towards a node, which is indicated by the black arrows here at the top of this image. While in the case of a negative contrast factor, they are manipulated towards the pressure antinodes as indicated by the red arrows in this image. So it's the difference, the relative difference in density and compressibility between the particle and the medium plays a very important role in defining the magnitude and directionality of the radiation force. So let's consider some typical particles which are manipulated in acoustofluidic resonators and their physical properties, particularly their size in micrometer corresponding to the diameter. So for non-spherical particle, this would be an equivalent diameter, the density in kilograms over meter cubes, and the compressibility in Pascal to the -1, as well as the acoustofluidic contrast factor. So a first class of particles are polystyrene beads, which are often used to assess the functionality of a resonator once it has been developed. As you can see, the density of these particles of polystyrene is greater than the density of water. So in this case, we are assuming water liquid at 25 degrees as the surrounding medium, the suspension medium for our particles. And the compressibility is lower. So this overall results actually in a positive contrast factor, which means that polystyrene beads will be moved towards the pressure nodes of a standing wave field. If we consider now two types of blood cells, erythrocytes and lymphocytes, for the same reasons that I mentioned before for polystyrene beads, they will also be manipulated towards pressure nodes. However, they've got very different sizes, so they may be subject to significantly different acoustic radiation forces, as if you go up here and look at the expression of the axial radiation force that scales with the cube of the particle size, the particle radius. And E. coli, in turn, which are a type of bacterial species, they are much smaller than, for instance, red blood cells or several types and classes of mammalian cells, so they will be subject to much lower primary radiation forces. Another interesting class of particles is represented by gas microbubbles, which have been extensively discussed in previous talks by Professor Eleanor Stride. So these particles have a comparable size to the one of some biological cells, but they've got a much lower density and a much greater compressibility because of their gas core. So this can result in an overall negative acoustofluidic contrast factor. So in some cases, gas microbubbles can be driven to the pressure antinodes of a standing wave field. And finally, it's interesting as well to compare healthy cells with cancer cells. And in some cases, it can be noted that while they present similar density and size, they have differences in compressibility, which could potentially be used as a way of manipulating these particles in a different way and potentially separating them for rare cancer cell detection. So the axial force that we discussed before is a form of primary force. So it's a force that originates from the interaction between the sound field scattered by the particles and the ultrasonic standing wave field itself. Another form of primary radiation force is represented by primary lateral forces. So there are forces that we tend to aggregate particles at a pressure node, so they will act in a direction perpendicular to the direction of wave propagation. We won't go through the mathematical derivation of this force, but it's important to note that this lateral radiation force is dependent upon the particle volume as well as the spatial gradient of the acoustic energy density. There is also a type of secondary force which doesn't result from the interaction between the ultrasonic standing wave field and the field scattered and the sound waves scattered by the particles, but instead results from the interaction of the scattered field between neighboring particles. And this type of forces, as referred to as secondary or Birkner forces, they also result in a net effect of aggregating particles at a pressure node, but they scale with the 6th power of the radius, and they can increase significantly with reducing interparticle distance. So in many cases, with increasing the particle concentration. So acoustofluidic resonators can be built in many different ways. So there are many different ways in which this type of acoustic standing wave fields can be generated within a microfluidic cavity. Two of such classes are layer resonators and transversal resonators. So layer resonators comprise different layers, each with a specific function and typically made of different materials. So these layers include a transducer that generates the ultrasound wave, a coupling layer to couple the transducer with the matching layer in gray here. The matching layer carries the wave into the fluid layer and also acts as a separation, as a physical barrier between the fluid layer and the transducer itself. Then a fluid layer with the particles in suspension. And finally, a reflector layer which reflects the wave backwards, generating a standing wave field. So in these particular types of resonators, the ultrasonic standing wave field is in the same direction of actuation of the ultrasound transducer, which generally is in the kind of in the thickness direction of the resonator itself. Transversal resonators instead generate a standing wave field which is perpendicular to the primary direction of actuation of the transducer, and that is an effect of the geometry of the structure and the material properties. In this presentation, we'll be primarily focusing on layer resonators. There are also other classes of resonators, such as surface acoustic wave resonators, but they're not described in this presentation. So we should also mention that in a layer resonator, the reflector and transducer layers are also air-packed, okay? And upon activation of the transducer, a one-dimensional resonance pattern is established along the axis of the acoustic field, which leads to the formation of an ultrasonic standing wave within the fluid cavity. And based on what we said before, particles in suspension within the fluid may be manipulated towards pressure nodes or pressure antinodes, depending on the acoustophoretic contrast factor. So the fluid layer of a typical layer resonator is in the order of 100 to 500 micrometers in thickness. Typical ultrasound frequencies range between 0.5 and 10 megahertz, and particle diameters between 1 and 20 micrometers, but that would largely depend on the application. So this video illustrates the manipulation of 2 micrometer polystyrene beads towards the center of a fluid cavity where an ALF wave resonance is established. So how are the materials that constitute a layer resonator chosen? So different criteria are typically applied, including their acoustic performance, their cost, the optical transparency, particularly if one wants to couple the device with an optical microscope, the manufacturability, so the ability of manufacturing complex channel architectures, the biocompatibility, if applications are involving biological cells, as well as the compatibility with chemicals and different classes of solvents. So this table provides a summary of typical materials used for the different layers of a layer resonator. And for each material, we have values of density, speed of sound, and also characteristic acoustic impedance. As you can see, the ultrasound source is typically a piezoelectric transducer, which has an impedance of around 35 kilogram over meter squared per second. But the carrier layer material can vary. In many cases, the impedance of the carrier layer is chosen to be between the impedance of the ultrasound source and the impedance of the fluid, which in this case is water liquid at 25 degrees. And that's chosen as a compromise to ensure a sufficiently high transmission from the ultrasound source into the carrier, and also to minimize reflections at the carrier fluid interface. As you can see here, different materials can be used as the constitutive material for the carrier layer. In some cases, polymers are used, but they present a much lower acoustic impedance compared to materials such as aluminum or machinable ceramics. And finally, if the reflector layer is often a glass layer, so a glass slide or cover slip, which has an acoustic impedance which is significantly greater than the impedance of the fluid layer, which results in a reflection backwards into the fluid layer to establish the standing wave field. It should be noted that in some cases, when the thickness of the reflector is much lower compared to the wavelength of the sound wave, the reflector doesn't act as an effective reflector. So most of the wave actually travels through the reflector layer, and at that point, it will be reflected backwards at the reflector air interface as opposed to the liquid, so the fluid reflector interface. And since there is a significant impedance mismatch between the reflector and air, that reflection will be very effective. So resonators can be manufactured in many different ways. Transversal resonators are often manufactured using chemical etching into a silicon substrate, for example. But layer resonators often bring together an assembly of micro meshing components, including, for example, a ceramic carrier, where the fluid layer is micro-milled, and PDMS gasket, which is a silicon gasket to basically generate a water-sealed environment for the fluid layer, and then a glass reflector. But glass capillaries can also be coupled with a piezoelectric element, and they can act as an effective resonator. So we mentioned some of these resonator configurations earlier. One popular configuration is represented by half-wave resonators, whereby the thickness of the fluid layer is approximately equal to half the wavelength of the ultrasound field. And in this case, particles with a positive contrast factor will be manipulated towards approximately the center of the fluid layer, so at the pressure node. Quarter wave resonators instead have a thickness of the fluid layer which is approximately a quarter of a wavelength. So in this case, the pressure node is located nearby the reflector, so particles will be manipulated in proximity to the reflector. And finally, THIN-REFLECTOR resonators are a class of resonators, as we discussed before, where the thickness of the reflector and of the fluid layer are much smaller when compared to the wavelength. So in this case, the reflector is not an efficient reflector per se, but most of the reflection occurs at the reflector air boundary. And this results in particles being moved towards the reflector air boundary, so ultimately being pushed in contact with the glass reflector surface. So let's now describe some examples of how acoustic radiation forces can be used for different applications. And one of such applications is particle or cell separation. So this particular example, a device with 3 inlets and 3 outlets has been designed, where in the central inlet, a buffer is injected, while in the 2 lateral inlets, a suspension of both blood cells and bacteria, where blood cells are significantly larger than bacteria. Before ultrasound applications, considering that the fluid undergoes a laminar flow regime, the different streams flow in parallel to each other. So the suspension of cells will flow towards these lateral outlets, while the buffer will continue to flow in the central outlet. If a standing wave field is applied, and particularly an half-wave resonance, what will happen is that because red blood cells will be subject to greater primary radiation forces, they will be moving towards the nodal plane at a faster rate and be then extracted through the central outlet, while the bacterial cells subject to a lower force that will carry on flowing towards the lateral outlet. This is a very convenient way of separating bacteria from cells, for example, in applications such as early stage detection of infections. Similar outcomes can be achieved using a quarter wave resonator. So this is a slightly different configuration, as we said before. In this case, the pressure node is located just below the reflector surface. So in this particular device, a suspension of both 5 micrometer and 2 micrometer in diameter polystyrene beads was injected in the resonator. And the larger particles, again, will be subject to greater radiation forces. So they will be moving more rapidly towards the pressure node, and they will be flowing towards the second outlet for extraction. The smaller particles will be subject to a lower magnitude of radiation force, so they will continue flowing towards this first outlet. So if we use an optical fluorescent microscope and we look down into the device, into this first outlet, you can see that the smaller particles in red are driven into the first outlet here very effectively, while the larger particles will carry on moving above the outlet towards the second outlet for effective separation between the two. It's also possible to couple acoustofluidic manipulation of particles with optical systems and high resolution systems to enable high throughput detection of rare particles or biological cells. For example, one can build an half-wave resonator coupled with an optical systems whereby the nodal plane of the half-wave resonator coincides with the focal plane of the optical system. So in this way, one can actually capture images of flowing particles that are all manipulated in the acoustic and optical focal planes. As you can see, when ultrasound is off, the particles are in different set positions, but when the ultrasound is activated, all the particles move in the pressure nodal plane, which is also the optical focus plane. So this method allows high throughput detection of particles and has been used, for example, as a proof of concept to capture images of beads up to 200,000 beats per second, but also of rare circulating tumor cells up to 60,000 cells per second. And finally, a final class of resonators, which we also mentioned before, are THIN-REFLECTOR resonators. So these type of resonators can also be used as an effective way of pushing particle towards a surface, either for enriching a sample, which includes like a rare organism, such as bacteria in this case, or for trapping or capturing particles over a surface for biodetection in situ. In this particular case, the THIN-REFLECTOR mode will push particles towards the glass-air interface, so particles will be flowing in contact or in close proximity to the reflector surface. And this is evident by using again a fluorescent microscope and looking at fluorescently labeled bacteria above the transducer. And as you can see, by moving from the carrier all the way up into the reflector, you can see that most of the bacteria are located at the reflector surface. And once they are at the surface, they can be then extracted from a dedicated outlet at much higher concentration. And if we now focus in this position exactly, so at the outlet, you can see that there is a high concentration of bacteria flowing over the surface of the reflector, and they also form these lateral bands, likely due to primary lateral radiation forces. And this system is a very effective configuration to actually enrich a sample that includes, for example, small amounts of particles or microorganisms. So in an ideal situation, as we discussed at the very beginning of this talk, the time average particle displacement, so the net fluid flow, is 0 everywhere. But in a real situation, viscous attenuation occurs, which may cause the net displacement of the fluid's particles during each oscillation cycle to become non-zero. And this may then result in the formation of streaming flows. So acoustic streaming is defined as a steady fluid flow formed by viscous attenuation of an acoustic wave. And depending on the mechanism of attenuation, streaming can have a range of fluid velocities from micrometer per second to centimeter per second. It can encompass a range of length scales from micrometers to centimeters, as well as can undergo different patterns like jet-like or vertical flows. So now we will just cover very briefly some types of acoustic streaming fields that may occur in an acoustofluidic resonator. And one of such types of streaming is represented by boundary layer streaming, which is labeled in orange here. So this is a streaming pattern which results from the viscous attenuation of the acoustic energy within the boundary layer of a resonator as the ultrasound wave travels parallel to the surface. So this boundary layer streaming is usually relatively strong, and then that would depend also on the frequency and the geometrical characteristics of the resonator. But in many cases, it is capable of driving a bulk motion of the surrounding fluid and set up a counter-rotating vertical flow, which is referred to as Rayleigh streaming. So in some resonators, both boundary layer streaming and Rayleigh streaming can occur simultaneously. Now, streaming can be deleterious for some applications. For example, it may disrupt the manipulation performance of a resonator in some cases, particularly when lateral forces play a primary role, but can enhance mixing and transport of chemical species and potentially induce mechanical stimulation of cells. So it can be beneficial in some applications involving, for example, cell culturing and stimulation. So this leads to the second area of application of acoustofluidic resonators, which is the one dealing with therapeutic applications, including drug delivery, tissue engineering, and therapy monitoring as examples. So in an attempt to classify the different types of stimulatory mechanisms or factors that a cells trapped within an ultrasonic standing wave field may be subject to, I've identified two classes of mechanisms. So primary mechanisms, which include the acoustic radiation force mediated deformation of a cell at the nodal plane of a standing wave field, in this case an ARF wave field. the steady state shear stress generated by the surrounding streaming patterns, and also potentially some oscillatory shear stress fields which could be generated by time modulation of the ultrasound field. Secondary mechanisms of stimulation may include convective heat transfer due to the heating of the transducer, as well as cavitation-mediated effects due to dissolved gases present within the fluid or exogenous agents such as gas microbubbles. And these effects have been extensively discussed in a previous talk by Professor Stride. So it's important also to note that this type of mechanostimulatory effect can occur on a single cell, but also on a cell aggregate. So there are types of resonators where lateral forces, either in the form of primary lateral forces or secondary Bjerknet forces, are particularly strong. So this will lead to the formation of multicellular construct, which can then be subject to the type of stimulatory effects I mentioned before. So previous studies have reported that, for example, single cells can be significantly deformed by acoustic radiation forces in a glass capillary type of resonator at relatively high frequency of, in this case, 7.9 megahertz. And remember, there is a dependence of the primary radiation force on the frequency of the ultrasound wave. So in this case, swollen red blood cells were basically squashed by radiation forces to an aspect ratio of 1.3. So it's a relatively significant level of cell deformation. Interestingly, previous work using similar type of resonators had shown that simply by manipulating cells towards a pressure node, it is possible to enhance intracellular delivery of pharmacological compounds, in this case, the model drug luteolin. And this delivery is dependent upon the ultrasound stimulation time, as well as the driving voltage of the transducer. But ultimately, enhanced delivery may be a result of deformational effects, as well as acoustic streaming. So in many of the applications reported before, devices were run at a fixed resonance frequency. In some cases, it's also possible to sweep the frequency around the resonance frequency, so over a range delta F. So for example, from F1 equal to the resonance frequency minus delta F, all the way to F2 equal to resonance frequency plus delta F, which passes through the resonance frequency. So this type of frequency modulation leads to perturbations of the acoustic energy density field within the fluid cavity of the resonator, which in turn leads to a lateral displacement of a single cell or a cell aggregate. So it can be used as a convenient way of generating oscillatory types of shear stress. Interestingly, it's also possible to change the frequency with which this frequency sweeping is carried out, and this will have an effect on the nature of oscillatory motion induced on the cells in suspension. So for example, if we apply a 20 Hz sweep rate on a cell aggregate, in this case, cells are fluorescently labeled and visualized using a microscope, you can see that the displacement is in the order of 3 micrometer, but at lower sweep rates, so we are sweeping at a lower frequency across, between F1 and F2 and vice versa. In this case, lower sweep rates result in greater displacements of the cell aggregate. So the overall effect is the generation of an oscillatory shear stress pattern, which can potentially be used to impart, biologically favorable effects. And interestingly, it can be modulated, for example, by varying the sweep repetition rate. So slower sweep repetition rates correspond to greater maximum shear stress values. Interestingly, these values are in the order of few megapascal, while the shear stress generated by the streaming flows that we described before are in the order of 13 micropascal in this particular study. Also, the shear stress magnitude can be modulated by changing the driving voltage, so the acoustic pressure. So it is a convenient system to impart a range of dynamical shear stress fields over biological samples, and it has been applied to the generation of tissue engineering constructs. In this study, in particular, human articular chondrocytes were cultured for 21 days in suspension within an acoustofluidic cavity and subject to that type of oscillatory motion. And interestingly, by analyzing the sample that is extracted after culturing and comparing samples which have been exposed to different frequency sweep rates, one can observe that samples which were subject to lower sweep rates, which were the ones corresponding to greater displacement and greater shear stress magnitude, had greater expression of chondrogenic factors, which are an indication of healthy tissue. Vice versa, this condition also resulted in the expression of the less desirable collagen 1 and collagen 10. But by combining the mechanostimulatory effect of a low sweep rate regime with a pharmacological treatment using a parathyroid hormone protein, one could obtain a healthy cartilage tissue which could be potentially implanted into a cartilage defect. A final application of acoustofluidic resonators is in therapy monitoring. This is a much more recent application and relies on a different type of design criteria for the resonator. So many of the resonators that we presented before strongly rely on pressure gradients within the fluid cavity and on the presence of one or more pressure nodes or antinodes where particles or cells are manipulated. One can also build an acoustofluidic resonator to basically have a relatively uniform pressure field within the fluid layer, as indicated by this graph here, which describes the acoustic pressure all the way from the transducer into the carrier, all the way from the transducer into the carrier layer here in blue, the fluid layer in light blue, and the reflector in black. As you can see, this uniform pressure can be generated by fine-tuning of the material properties and the thickness of the layers of the resonator. This type of resonators could be used, for example, to assess the effect of ultrasound stimulation on ultrasound responsive particles, such as gas microbubbles, as well as the interaction between microbubbles and biological cells in situ. So this type of analysis can also be performed with a variety of macroscale systems. The potential added benefit of an acoustofluidic resonator is its ability to be coupled with high resolution optical and also other type of detection systems that, for example, enable characterization of the cavitation microstreaming pattern generated by a gas microbubble. In this case, they are visualized using fluorescent particles as flow tracers within the fluid cavity. And this type of analysis can also lead to the quantification of the streaming velocity using methods such as particle strip velocimetry. But they can also be integrated with sensors to detect cavitation activity. So practically the frequency content of the oscillation that is, the volumetric oscillation to which microbubbles are subject to when exposed to an ultrasound field. And potentially they can also be coupled with ultra high speed imaging techniques to actually quantify the volumetric oscillations that bubbles undergo upon ultrasound stimulation. So this is a relatively recent area of research that potentially also enables the investigation of the biological effects of these physical mechanisms on biological cells, both kind of on cell monolayers as well as tissue mimicking phantoms. In conclusion, acoustic radiation forces within an ultrasonic standing wave field can drive particles towards desired location in a microfluidic cavity. There are different classes of acoustofluidic devices, which comprise different constitutive materials and also different resonance configurations depending on the application. And finally, acoustofluidic resonators can impart different forms of mechanical stimuli, both steady state and time dependent on both cells and tissues, with potential for application in drug delivery and tissue engineering. So in conclusion, in addition to the different references that were mentioned along the presentation, if you are approaching the field of acoustofluidics, I highly recommend reading the Acoustofluidics series. And particularly, there are articles that deal specifically with the design, modeling, construction, and also biological compatibility of acoustofluidic resonators. And thank you very much for your attention.